Everybody, dealing with Math 158, section 5.1. In this section, we're going to be talking about operations of matrices. We're going to be talking about matrix equality, matrix addition and subtraction, and the transposition of matrices. Okay, first thing we're going to start off with is we're going to start off with matrix equality. Okay, for matrix equality, for two matrices to be equal, they have to have the exact same dimensions. They have the same rows and columns for them to be equal. So we're going to set up a little problem. We have x, y plus 1, -2, and 4. And then we're going to set that equal to the matrix 8, 5, 3z plus 1, and x plus w. Yes, matrices are allowed to have variables in it. What we have to understand about matrix equality is the terms or the entries that are in the same corresponding positions are equal. So in this case, row 1, column 1 of the first matrix is equal to row 1, column 1 of the second matrix. So we can say here that x equals 8. Right. We go over to row 1, column 2. We can say that y plus 1 equals 5. And we can solve that down by subtracting 1. And we can say that y would equal 4. We go to row 2, column 1 would be equal to row 2, column 1 of the second matrix. So -2 equals 3z plus 1. So I would subtract 1. -3 equals 3z. Divide by 3. -3 divided by 3 is -1. And -1 equals z, or z equals -1. Our last entry here would be row 2, column 2. So row 2, column 2 would say that 4 equals x plus w. Now this has two variables in it, x and w. This x, since it's all in the same problem, is all related. So we already have an x value of 8. So we can plug that in and say that 4 equals 8 plus w. So we would subtract that x at -8, and we would have -4 equals w. So we have just solved these two matrices, right? Matrix equality. So our corresponding entries of our equivalent dimension matrices would be equal to solve down for our variables. And that's matrix equality. Obviously, we can make the problem harder by putting more terms in, but it's the same thing no matter how many terms that we have. So for addition and subtraction of matrices, pretty simple, pretty similar to the matrix equality. Corresponding parts of these two matrices need to be added together. Make sure you look at the sign in the middle of the matrices. This one we have addition. So what we're going to be doing is we're going to be adding the corresponding parts. So row 1, column 1 is going to be add an addition or the sum of row 1, column 1 of these two. So that's going to be 2 plus 9. Then row 2, column 1 would be 1 plus 0. Row 3, column 1 would be -1 plus -1. Then row 1, column 2 would be -3 plus -5. Row 2, column 2 would be 0 plus 13. And row 3, column 2 would be 3 plus 3. So 2 plus 9 would be 11. Negative 3 plus negative 5 would be negative 8. 1 plus 0, 1. 0 plus 13, 13. Negative 1 plus negative 1, negative 2. 3 plus 3, 6. Obviously, you don't have to do this middle step. You can kind of do this in your head. You could just add those corresponding parts together. I did this to show you my work, my thought process going through it. Subtraction, same thing here, okay? We are just subtracting the corresponding parts. So we would have 2 minus 9, negative 3 minus negative 5, 1 minus 0, 0 minus 13, negative 1 minus negative 1, and 3 minus 3. So we look at this, and we actually subtract those. 2 minus 9 would be negative 7. Negative 3 minus negative 5, so we're subtracting a negative, so we have to add. So that would be 2. 1 minus 0, 1. 0 minus 13, negative 13. Negative 1 minus negative 1 would be 0, and 3 minus 3 would also be 0. Another thing I wanted to show you is that just like typical numbers, it matters the order of subtraction. It doesn't matter the order of addition, it matters the order of subtraction. So if I did the same thing here, but I switched the order of these matrices, how would that affect my final answer? So instead of the first matrix going first and the second matrix going second, I'm going to flip-flop them. So 9, negative 5, 0, 13, negative 1, 3, minus 2, 1, negative 1, negative 3, 0, 3. So 9 minus 2, 0 minus 1, negative 1 minus negative 1, negative 5 minus negative 3, 13 minus 0, and 3 minus 3. So 9 minus 2 would be 7, 0 minus 1, negative 1, negative 1 minus negative 1 would be 0, negative 5 minus negative 3, that would be negative 5 plus 3, which would be negative 2, 13 minus 0 would be 13, and 3 minus 3 is still 0. Comparing these, what do you notice? The entries are opposites. So this was negative 7, that's 7, 2, negative 2, 1, negative 1, negative 13, positive 13. So it does matter the order of subtraction, just like 2 minus 3 is not the same as 3 minus 2. I wanted to quickly show you another problem of something that might come up. Here we have a matrix and, well, two matrices being added together. Might look a little odd to you, and it should. The dimensions of this are a 2 by 3 matrix. We have 2 rows, 3 columns, but this matrix has 3 rows and only 2 columns. So this is a 2 by 3, and this is a 3 by 2. Can we add these together? The answer is we cannot. So you can't add together matrices that do not have the same dimensions. If this comes up, you ever see this, you just say you cannot add. You can't do it. So you cannot add. Okay. So you have to have the same dimensions in order to add or subtract. So I wanted to show you an example from your textbook. So if you have your textbook in front of you, and you want to look at example 2 on page 325, I'll explain kind of the gist of the problem for you. We're dealing with an auto parts store. that is looking at their sales from 2 different locations in January and February. The textbook problem gives this data in 2 tables set up the same way. So therefore that this 20 and this 23 correspond to the same item being sold in the same location. So I set these up into 2 different matrices. We have J standing for January and F standing for February. What they want to do is they want us to figure out the difference or how much sales have changed. So the difference of February to January, what the actual sales difference was. So if we want to find the difference, we take the second and subtract the first. So what they want us to do is they want us to take matrix F and they want us to subtract matrix J. I don't know if I've mentioned it in the past, but matrices are represented with capital letters. So this would be matrix J representing that, matrix F representing that for January and February. I could have picked A and B, X and Y. So when we are talking about the operations of them, I would just say F minus J, and you knew that I was talking about this matrix, subtracting that matrix. So F minus J would be 23 minus 20, 8 minus 10, 4 minus 8. And this would be 12 minus 15, 12 minus 12, and 5 minus 4. So the resulting matrix of this subtraction, we would have 3, negative 2, negative 4, negative 3, 0, and 1. So if you look at the context of this problem, the columns of the tables both represented the locations. I believe we had Vancouver and Quebec. And the rows represented 3 different parts that the auto shop sold. We had wiper blades. Wiper blades. Then we had cleaning fluid. And floor mats. All very essential things in the winter. All right, so what does this resulting table means? It means, so we're talking about the change in, we went up 3 wiper blades more in Vancouver. We went down 2 cleaning fluids, and we went down 4 floor mats from January to February. We went down in Quebec 3 wiper blades, didn't change at all cleaning fluid in Quebec, and we went up 1 floor mat. This can definitely be useful for you in the business world, taking tables and adding and subtracting and performing operations with large matrices, large table sets. I always think of this as those of you that are familiar with Excel, doing macros in Excel. Very similar to this. Understanding matrix operations will help you a lot with when you're creating macros in Excel and other table software. I'm sure Google Sheets does it as well. All right, next we're going to be dealing with some scalar multiplication. Scalar multiplication, what they're going to do is they're going to give you a particular matrix. In this case, we're just calling it matrix M. Matrix M would be a 3 by 2. It doesn't matter what the dimensions of the matrix are. They're now asking us to find 6M. So they want us to take the matrix M and multiply it by 6. Scalar multiplication, we're making all the entries larger. So what they want us to do is take 6 and multiply it, everything in the matrix, by 6. Okay. So 6 times 5 halves. So that'd be 6 over 1 times 5 over 2. So that would be 30 over 2 would be 15. 6 times negative 3 would be negative 18. 6 times 1, 6. 6 times 0, 0. 6 times negative 1, negative 6. And 6 times 5/6 would be 5. So matrix M being multiplied by 6, everything in it gets multiplied by 6, and that's scalar multiplication. There is no such thing as scalar division, but what you can do is you can multiply by a number less than 1, which makes things smaller. So example 3. On page 326 in your book, they are talking about that same auto parts store, the same sales, the same matrices, actually a little bit different matrices. We are dealing with matrix C. So we have Canadian dollars here. We have 140, 30, 96, and 105, 36, and 48. If you read the problem, what these are the sales in Canadian dollars. So that would be, I believe this column still represents Vancouver, this column represents Quebec, and the 3 items of wiper blades, cleaning fluids, and floor mats. But they want to send the data to the United States, so they want to convert it to US dollars. So the US dollars, they have the conversion rate that they give you would be 0.65. So dollars would be 0.65 times C. So we're dealing with 0.65 times C. Because 0.65, this number is less than 1, these numbers are going to decrease. So that would be the same as division. So we're dealing with 0.65 times our matrix of 140, 30, 96, 105, 36, and 48. If we take each of these terms and multiply it by 0.65, we would get 91, $19.50, 19.50, 62.40, and 68.25. Sorry for it being squished. 23.40 and 31.20. So what that would mean would then something that was worth 140 Canadian dollars would be worth 91 US dollars or American dollars. So what we did is we just used the same scalar multiplication to then change all of these over pretty quickly, deal with data sets. There are programs or your calculator can do this for you. I'm showing you how to do it by hand just so you understand it. All right, next we are going to move on to a little thing called transposition of matrices. Transposition of matrices is a pretty simple concept. If I wasn't here showing it to you and you saw it on a piece of paper, you might get a little confused about what is actually happening. What a transposition of a matrix is you would switch the columns of a matrices with the rows. So row 1 becomes column 1, row 2 becomes column 2, and row 3 becomes column 3. I guess you could do it the other way and say that column 1 would become row 1. It would all work out. All right, so the symbol for transposition is you would have a little T above the letter that represents the matrix. So if you ever see A with a T above it or any letter with a T above it, that means that you have to find the transposition of that matrix. So the transposition of matrix A that we have here. Matrix A is a 3 by 4. The transposition is going to end up being a 4 by 3. We're switching rows with columns. So I go along this first row is going to become the first column. So instead of going across, I'm going to go down. So this is going to be 2, 0, 1, 0. So first row becomes first column. Second row becomes the second column. So 33, negative 22, 0, and 5. And the third row becomes the third column. 1, negative 1, 2, negative 2. So we have matrix A and the transposition of matrix A. Row 1, column 1. Row 2 becomes column 2. Row 3 becomes column 3. Why is this necessary? This is necessary to do sometimes to get the matrices to have the same dimensions so you can add and subtract them together. So you can multiply them together and things like that. So transposition of matrices. Okay, so let's recap all that we did in section 5.1 with a little bit of practice. So in this practice, we're going to be using these same 3 matrices. So I'm telling you that matrix A is this 3 by 2 matrix. Matrix B is this 3 by 2 matrix. And matrix C would be this 2 by 3 matrix. The first question I'm going to ask is, what is B plus 3A? So here we have some matrix addition. We also have 3A. So that's going to be a scalar multiplication of matrix A. So matrix B is what we start with. And that's going to be 5, 3, 0, negative 1, 2, negative 4. And that's going to be added to 3A. We could write 3A out in a step, but I'm going to go through and I'm just actually going to multiply it. So 3A would be 1 times 3, which would be 3. 3 times 3, 9. 3 times negative 5 would be negative 15. Negative 2 times 3, negative 6. 4 times 3, 12. And 0 times 3, 0. So now we have B plus 3A. This is 3A, 3 times A. Now we just need to add the parts together. So we have 5 plus 3 would be 8, 3 plus 9, 12, 0 plus negative 15, negative 15, negative 1 plus negative 6, negative 7, 2 plus 12, 14, and negative 4 plus 0 would be negative 4. Okay. As you can see, there's no particular order that I'm adding these together in. I could add in any entry at any time. Sometimes I find myself going down a column or across a row. It doesn't matter how you do it as long as you keep the corresponding parts together. Our next problem, I'm going to keep these same 3 matrices, but I'm going to have a little different matrix equation here, or matrix expression here for us to solve. Our new equation number 2, or new expression number 2 would be the transposition of matrix C minus 2B. I have to transpose C. If I didn't use the transposition of C, I wouldn't be able to subtract these together because they wouldn't have the same dimensions, right? C is a 3 by 2 and B is a 2 by 3, or sorry, B is a 3 by 2 and C is a 2 by 3. We do rows and columns. So C of T, so I have to take the transposition of C. So that first row becomes the first column. So the first row, 0, negative 1, 2, becomes the first column, 0, negative 1, 2. The second row becomes the second column. So -5, 3, -4. And that's going to be subtracted from 2 times b. So 2 times b would be 10, 6, 0, -2, 4, -8. Now to subtract them, just going to subtract the corresponding parts. So 0 minus 10 would be -10, -1 minus 6, -7, 2 minus 0, 2, -5 minus -2 would be -5 plus 2. When you're subtracting a negative, you add the opposite. So -5 plus 2 would be -3. 3 minus 4, -1, -4 minus -8 would be -4 plus 8, which would be 4. Okay. You might see something else added on to the end. You might see a third one. If I chose to then change this and say, well, add on A to this, and you have 3 things, do it like you would a normal problem, okay? Subtract the first 2, and then add on A. So I can add on A here of 1, 3, -5, -2, 4, 0. And then the result would be -1 plus, or sorry, -10 plus 1 would be -9. -3 plus -2 is -5. -7 plus 3, -4. -1 plus 4, 3. 2 plus -5, -3. 4 plus 0 would be 4. Okay. I'm sorry if that confused you. I decided to just add on that A. That was kind of last minute thing. So that is all of 5.1. Make sure you check out 5.2 video as well. That's going to be all on multiplying matrices together, which does get a little complicated. So check out that video as well on 5.2.